speaker for this morning is Rafael Cottom, who has joined us from Santa Barbara City College this summer. He's been working with Erika, and he'll tell us about their project together, deriving the first stellar mass distribution from the light element abundances of metal-poor stars.
Thank you for that introduction, Gwen. So the research I've been doing this summer with Erika can be thought of as stellar ancestry. Much like ourselves as humans, we have ancestors, stars have ancestors too. But what do we mean when we say a star's ancestor? We're referring to the progenitor star. So let's go into that. Where does their story begin? It begins with all good stories, where all good stories begin, with the Big Bang. After the Big Bang, we saw hydrogen, helium, and trace amounts of lithium in the universe, and from those primordial elements, the first stars came about. These stars, as denoted by this right here, have zero metallicity. Their metallicity is equal to 0. Now, the massive ones of those that were massive enough to erupt in supernovae, as they died, to explode, excuse me, did so. And as they did so, they released heavier elements into the universe, and specifically into the gas surrounding them. From that gas, later on, were the second generation of stars born. These are referred to as population 2 stars. And the first ones are counterintuitively known as population 3 stars. It's in backwards. So these stars, as you can see right here, are known as metal-poor stars. So these are the stars that we're studying. Now, in general, there are many elements in the universe that I did not use in my project. And this is an excellent periodic table by Jennifer Johnson that goes into where some of the other elements come from. The ones that I was concerned about this summer are as a result of exploding massive stars. So the ones that I used pretty much ended at zinc. Now, what's the motivation for all this work? What can we hope to gain from all the work that we're doing this summer? Well, we believe that the stars that we're studying are the remnants of a small galaxy-type entity from outside of our galaxy that was assimilated into our own galaxy, or accreted, you might say. So this is an image from Gaia showing you several dwarf galaxies and globular clusters that potentially resembled the body that is the origin of the stars that we're studying today. And these lines that you see here are their paths that they've traveled. But after a long time of doing so, some of these bodies, they get augmented, they get disrupted by the Milky Way galaxy. And as they do so, as you've heard before from Bridget and Sylvia, and you will hear from Tiffany about this, they become what we know as stellar streams. So they change shape. Following that, they become assimilated or accreted into our galaxy. The stars that I'm looking at have already gone through that process and are now within our galaxy, in the galactic halo, precisely. So here's the question. How do we use those remnants of those small galaxies to study the ancestors of the metal-poor stars? Now, how did we select what we're working with? So there was a paper by Goudin et al. Not too long ago that tagged 30 or so groups of stars based on their chemical and dynamical similarities. So the ones that we're looking at are in this red box right here. This is CDTG14. That is the name of the group of stars that I've been studying. Again, they were tagged based on their chemical, so their elemental similarities, as well as their dynamical properties, the way they're moving through the galaxy. What did we do with the data that we collected? We used a software called Spectroscopy Made Harder. I see it is not visible at the top of the screen, but that's all right. Spectroscopy Made Harder does an equivalent with analysis. So using this application, we were able to derive the elemental abundances, which can be seen in this little red rectangle right here, for a variety of elements that we collectively know as light elements. Following this, we were able to plot all of them together in a plot much like this one. And this one is just the elemental charge number here on the bottom and the abundances of the elements. Now, in order to continue the project, or the next step, I should say, we used an application called StarFit. StarFit took our elemental abundances and said, okay, for those abundances of those elements, this is what the 10 most likely stars that enriched your star that you're observing today looked like. So these are 10 different models. They are in rows. The column that we're most interested in is this column right here, the mass. Because again, harkening back to the title of this presentation, it's the mass distribution of the progenitor stars of these metal poor stars that we're studying today. So we're interested in the mass. And just to show you visually, this is one model. StarFit, as you see, gives you more than just the mass of the progenitor star that potentially enriched the star that you're looking at today. It includes energy and dilution. And over on the left-hand side over here, chi-squared, this column refers to the likelihood. So the lowest chi-squared is StarFit's most likely model. Now we're able to plot the abundances and the models together. Here are just a couple of the models for this specific star right here, which has a very memorable name. Now, these in white are the abundances of the elements in that star, and the two models that have been fit to it, one of them, the one that's above in blue over here, is an 18.5 solar mass model, and the one below it in a redder color is 100 solar masses. So again, StarFit is saying, listen, these stars of these masses potentially enriched the star that you're looking at, this star right here. Which one is a better fit? It's going to be the 100 solar mass model. As we see in a second, for this specific star, StarFit believes that the most likely mass of a progenitor star is 100 solar masses. And the third most likely is 18.5 solar masses. So here is sort of the fruit of our labor, a magical plot that we created not too long ago with some of the stars of our sample. So this is not referring to the error bars. However, where the field is thicker, there are more models. StarFit believes that it is more likely that this mass of a star is correct for a progenitor star. This is the population 3 stellar mass against the metallicity of the population 2 star. And where there are fewer models, the field is thinner. And where you see a star is StarFit's most likely model for the mass of a star that enriched those stars. And so from here, we notice something pretty interesting. If you notice, a lot of these most likely models for the stars of lower metallicities are around 26 solar masses. So from this, we see that it's interesting that most of these low metallicity stars appear to have been enriched by a star of approximately 26 solar masses. And from there, just to sum up again, what I did this summer was I looked at the elemental abundances of a group of population 2 stars that are referred to as metal poor stars. And using those, we derived the approximate mass of their ancestors. And what we found was, like I showed you just now, that most of them appear to have been enriched by a star of approximately 26 solar masses, which is significant. I personally did not expect to find that. And something that we're going to do in the future is we're going to derive the carbon abundances, which is a slightly different process for the rest of the stars in our sample, as well as perform a similar analysis using Gaia DR3 data and compare that to the StarFit's results that we had. So thank you, and I'll answer any questions.
All right, very nice. Questions for Rafael?
Okay, we have a question from Andy McWilliam. Are these evolved stars? In that case,
Sorry, one more time?
Question from Andy McWilliam. Are these evolved stars? In that case, the carbon and nitrogen abundances will be modified and the CO not immediately useful to estimate a mass of the supernova 2 progenitor. Is that a question or a comment? All right, I guess question, are these evolved stars?
I am not familiar with that term, so I cannot comment on that.
Okay.
Other questions?
So the 100 solar mass star that is the better fit, that's a POP3 star, is that right?
Yes.
Okay, so I don't know who models those. Are there any When I was last looking at this, people did not have good models of 100 solar mass stars with no metals. Who's doing that, and how reliable are those?
So the models that we're using, the abundance pattern models for population 3 stars that we're using, came from Alexander Hager et al. They gave us the software. They produced the software, which included several different models. More about that, I'm not sure, but we're using their models. Again, that's StarFit, to just using what they have. Yeah.
Other questions?
Yeah, I was wondering if you could talk more about like what these stars kind of look like.
Sure. I'd love to talk about what these stars look like. So the stars that I'm looking at, again, these are population 2 stars, around 10 to 11 billion years old. They are much, much older than our star, about twice our star's age. Our star being a population 1 star too. So they are at pretty much the end of their lives. They're in their red giant phase. In fact, they are less massive than our own star. They're approximately 0.8 solar masses, so 80% the mass of the sun. And yeah, they've been alive for quite a long time. And they are the remnants that are observable, at least, that we can derive spectra for that pre-existing extragalactic entity that was accreted into our own galaxy.
So my question was, do you think 100 solar mass, the thing that you found, is kind of an outlier compared to the other ones? Like, because they were somewhere close to 26 solar masses, and this is the only one which is at 100 solar mass. So do you think is that an outlier for the sample that you were looking at?
Sort of. For our results, in a way, yes. But in general, population 3 stars were massive compared to the stars of population 2 stars, for example, more or less. So 100 solar masses is not outlandish for population 3 star. In fact, 26 is, from what I understand. Yes.
It's really nice. And I have a question about the Gaia DR3 data that you plan to use, because it seems like that will be a very different kind of data compared to the high resolution spectroscopy that you used so far. So can you tell us a little bit more about those plans?
Well, Gaia would have given us calcium triplet in the calcium triplet wavelength data. So our analysis would have to involve just that part of the light spectrum from any given star. That's the extent of my knowledge on specifically what Gaia would, or what we would use from Gaia. But that analysis hasn't happened and would happen if we had more time and resources and so on. So perhaps in the future, not certain.
All right, let's thank Rafael.